In today's class, we're going to take what we know about the first and second derivative and apply it to making quick sketches of functions. The graph of a function can be determined, you can draw it, based on what's happening with the first and second derivatives, assuming that we have a normal curve. Even if you don't know what the function is, it's possible to sketch a graph of what it is if you know enough about the first and the second derivatives. And that's what we're going to learn today. First, we'll start with the first derivative rule. Now, in looking at this particular graph, we'll begin to notice a pattern here. If we look at the relative extremes, in this case, let's look first here at the relative maximum. We realize here at x is equal to -2 that there's a relative maximum here. And if we look at the slope at this point, x is equal to -2, we realize that the slope is 0. Now, as we've defined many times before, the slope and the first derivative are the same thing. So, since the slope is 0, the first derivative is also equal to 0. Now, are there other places where we see the slope equal to 0? Well, yeah, if we come over here to this relative minimum and take the slope here, we realize that it's also a horizontal line. The slope will be 0, and that, of course, means that the first derivative is also equal to 0. So at these two places where there are relative extremes, we see that the slope is equal to 0. Now, is the slope equal to 0 any place else in this graph? Well, over here we realize the slope is going to be positive, but it's always going to be a value. It's not a horizontal line. It's not a flat line like this. In here it's going down, here it's going up. So these are the only two places where it is flat, so to speak, where the slope is 0. So that gives us the idea that whenever we're looking at a maximum and minimum, the slope for the first derivative will be equal to 0. So if we knew where the first derivative was equal to 0, then we would know that you'd have either a maximum or minimum at these locations. Now, looking at this particular graph, we can look at this and realize that there's a local minimum here. Now, if we were given the function for this x minus 1 the quantity squared, well, if we didn't have the graph, using the fact that the slope of the first derivative will be equal to 0, could we get an idea of where this is? Now we can multiply this out and know that it's going to be an x squared graph. But if we take the derivative of this, using again, since this is something inside of a parenthesis that's raised to a power, we could use that rule where we take the power times what's inside the parenthesis raised to a power that's 1 less than what originally was, times again the derivative of what's inside. The derivative of what's inside is simply 1. And of course then we would get 2 times the quantity x minus 1, which then if we multiply the 2 out, we would get 2x minus 2. Now if we set this equal to 0, this is where the first derivative would be equal to 0, since this is the first derivative. So 2x minus 2 equals 0. Now solve for x. Find out what the value of x is. Well, we're going to add 2 to both sides. We get 2x equals 2. Then we're going to divide both sides by 2 to get x is equal to 1. So even if we didn't have this graph over here, and we started with just this function, if we take the first derivative, set it equal to 0, we can find out where the local maximum or minimum is. And in this case, it's at x is equal to 1, and we know that it's going to be a minimum because it's a straight parabola, a standard parabola, I should say. Here we have a local minimum, and when we're working with this, we see that the function is decreasing, and then here the function is increasing after this. Now, the first derivative rule is a simple rule. It's going to help us to graph things. We've just figured out we can find where the relative extreme are, the relative maximums and minimums, but what about in between? Well, the first derivative rule says that if the first derivative is positive, then that means the slope is positive. We know that because we've learned that before. And of course, if the slope is positive, then we know that f of x is increasing. The slope of a function that's increasing, it's always going to be going up if it's positive. And if it's going up, if the slope at any particular point is going up, then the function has to be going up at some point. It can't be going down. Even if the curve was the other way, the function is still going up. If we take the slope all along here, it's going to be positive. Here it's going to be positive. Here it's going to be positive. It's always positive, so the function has to be increasing. So that's the first thing that we find. If the first derivative is positive, then the original function is increasing. Now, the opposite is also true. If you take the first derivative at a point and you find that it's negative, it's going down, that means, of course, there's a negative slope. If it's going down, for example, even up here, if you took a tangent line, it's going down. If you took it still here, if you took it here, it's still negative. It's still going down, it's still negative. So that must mean that the function is decreasing. And even if the curve was going the other way, like this, it's still decreasing. And when I say it's going the other way, here it's concave up, here it's concave down. The slope all along here is going to be negative, so that means it's going down. So the function will be decreasing. Now, there's a third case, and we've already kind of touched on this. If the first derivative is equal to 0, then usually that point is a relative extreme, either maximum or minimum. There are a few odd cases, and we're not really going to study them in this class because it doesn't often directly apply to business, so we won't worry about this. But there are a few strange cases where the first derivative is equal to 0, but it's not a relative extreme, so the function could be increasing or decreasing, and you have to do some other logical testing to figure out which it is. But again, we're not going to focus on that. In this class, if the first derivative is equal to 0, then it's going to be a relative extreme. Now, using what we know, can we sketch a graph here where we have an f of 3 equals 4? Well, if we have an f of 3 equals 4, well, that gives us a point, right? As in, if we put x into the equation, we get out a y. Well, in this case, our x is 3, and our y then is the answer that we get of 4. So we have a point at 3, 4. So if we come over 1, 2, 3, and 1, 2, 3, 4, we would put a point here. Now, the second part of it says, f prime of x is greater than 0. The first derivative is positive when x, or for when x is less than 3. So that's going to mean that when x is less than 3, it's going to be on this side of this point. The first derivative is positive, which means it's increasing. It's going up. And it's going to go up at least until you get to this point. So it's going to be going like this somehow. Well, we don't necessarily know what it would be yet. So let's maybe draw a little directional thing here saying that on this side, we know that it's going to go up. Oops. And then at f prime of 3, the first derivative at 3 is equal to 0. So we know here the slope is going to be 0. So we could draw in just the tangent line, so we know that this reminder that the slope is 0. And now the first derivative of x is less than 0, which means it's negative, when x is greater than 3. So on the other side, from 3 and greater, the first derivative is negative. The first derivative rule says then the function is decreasing. So we have this kind of thing happening. It's going down after that. So it must be going up from when it's from example, from the negative numbers up to 3, it's going to be increasing. And after 3, when x is equal to 3, it's going to be decreasing. Now, if the slope is 0, we kind of figure that more than likely, if we're going to draw the line of this, it's not that it's going to be a straight line to go straight up there and down, because that would be kind of a strange function. It's possible, but not real likely. So probably with this, the slope is going to be a bit more gradual of a change, and this is the high point. So if this is the high point, it may just want to kind of come down kind of like this. And we could have it do kind of the same thing on the other side. It's increasing from the negatives and so on. It's increasing up to 3 where it's a high point, and then it's decreasing from there. And if we look at the slopes, that kind of helps. Now this is a nice graph, but why could it not look like this? How do we know? On the original one, we had said that it was, when we drew it, it was concave down. Well, what if it looked like this? You have a strange kind of thing. Well, if we evaluate the slope around 3, x is equal to 3, that is, we can see what's happening. If we took the slope down here, well, the slope may be, well, say 1. If we took the slope here, the slope may be 2. Maybe the slope here is 3. The tangent line here, 4, 5, 6, maybe up to 10 until we get to here. So it's going 1, 2, 3, 4, 5, 6. The slope is going up to 10, maybe here, maybe even more than that. Well, then all of a sudden here, when x is equal to 3, the slope jumps from, well, let's just pretend it was, right before this point, it was 10. So if it was going up 1, 2, 5, 10, then all of a sudden it jumps to 0. But that's kind of a strange thing. And on this side, it's kind of reflexive, so we'd say if this was positive 10 over here, then this was, the slope's going down, it'd be like negative 10. And then it's going to count down to 5 and 2 and 1 and so on. So if you had a curve, would the slope really go from 1, 2, 3, 4, 7, 8, 10, 0, minus 10, and minus 5, minus 4, 3, 2, 1, and so on. So would it really do that kind of jumping? And we say, no, it probably wouldn't. So this kind of graph is not likely to happen. It is going to be more concave down like we did before. Now, as we're looking at this, we realize, well, do we have to graph this every way and evaluate it? Well, maybe there is another way to do this. And to figure this out, let's look at a standard parabola, f of x equals x squared. Now we know that it is concave up here all of the time, right? So if we had a graph that was concave up, what if we had a graph that was concave up all the time, it would be a parabola like this. Now if we take the first derivative of this, of x squared, we get 2x. Now if we put in the values of this, like we did earlier in class, from x is between negative 3 and positive 3 inclusive, then we could look at it and say, at x is equal to minus 3, the slope is going to be minus 6, and then it's minus 4, minus 2, 0, 2, 4, and 6. Hopefully this is a review, but it should make sense. Now we notice with this, the first derivative rule, that the slope is negative over here and it is decreasing. Then it becomes 0, and then of course the slope is positive, so it's increasing. And that's helpful. But what if we look at the second derivative? Well, if we look at the second derivative, the second derivative is the derivative of the first derivative. So if we take the derivative of 2x, we get simply 2. Now we notice that 2 is a positive number. So, and we, in fact, here, when it's the second derivative of x is equal to 2, that means it's 2 everywhere, for every point along this curve. The value everywhere at each and every point is positive. So we'd say that the second derivative is always going to be positive at every single point. Well, it's positive, and we look at this and say that it's concave up. So we can put these two together and realize that in this case, if the second derivative is positive, well, then it's concave up. If we take the inverse of this function, f of x is equal to minus x squared, the first derivative is going to be minus 2x. And again, we can do the evaluations, and we realize, yes, over here, the slope is going to be 6 and 4 and 2. And since it's positive, it's increasing till we get to this point, and then after it, it's going to be negative. 0, minus 2, minus 4, minus 6. And it's since the first derivative is negative, it's going to be decreasing here. But if we take the second derivative if we take the derivative of the first derivative, which is the second derivative, we get minus 2. Well, minus 2 is, of course, negative, and it's true that it's minus 2 for every point along this particular curve. And we notice that f of x is concave down over the entire curve. So we can put these two together and say, oh, well, if the second derivative is negative, then it's going to be concave down. Now that is simply the second derivative rule. If the first derivative is positive, then it's going to be concave up at that particular point or for that range. In the case before, using x squared or minus x squared, it's over the entire area, it was concave up or concave down. If the second derivative is negative, then the original function f of x will be concave down over that interval or at that point. Now, as you know, if you do a more complex graph, it can be concave, both concave up and concave down, not at the same place in the graph, but at different points of the graph for different ranges. And that's quite okay, it's quite normal. Now, we've covered when the second derivative is positive and when it's negative, and then, of course, you must have places where the second derivative is equal to 0. Well, then if it's equal to 0, it's not positive, it's not negative. So it's not going to be concave up or concave down at that point. And so usually this will be a point of inflection. Now, there are a few odd cases. Again, we're not necessarily going to get into them in this course. But if it's not a point of inflection, it could be either concave up or concave down. But for our purposes in working with business, it's going to be an inflection point. Now, how that would work, if we look at some of what is behind this, we realize that when the second derivative is equal to 0, as we just said, it's a point of inflection. If we looked at this graph, we'd say, oh, well, here, it's a point of inflection at x is equal to 4 here. Because before x is equal to 4, it's concave down. After x is equal to 4, it's concave up. So this must be a point of inflection. So if we look at a graph of the second derivative, we'll find this out. Now, this is also an exercise in understanding how, if we graph the derivative from the original function, what it would look like. The graph of the derivative is going to be a graph of the slope. So here, the y value, well, like here, when x is equal to 6, it's going to be above 25. But the slope here, when x is equal to 2, the slope is 6. So what they did then is on this graph of the first derivative, when x is equal to 2, you put in a point here. The value is the slope of the original graph. The slope here is 6, so you put in a point here at 6. At x is equal to 0, the slope is 18. The value is not 18, the y value is not 18, but the slope is. So they're drawing a tangent line and taking the slope of the tangent line and saying it's 18. So on a graph of the derivative, when x is equal to 0, you plot the value of the slope, which is 18. At x is equal to 4, the slope is 2, so at 4 you put a dot here at 2. And at 6, x is equal to 6, the y value is, well, closer to 40, but again, we're graphing the slope. So the slope is 6, so we put in a point here at 6. Now, when we're doing this then, we realize that the slope is pretty steep here, and it slowly decreases till it gets to this point. So it's going to come down, it's going to keep decreasing down to a value of 6 here when x is equal to 2, and then it keeps going down until this point of inflection when x is equal to 4. So it's the low point here, it's the smallest value, and then the slope starts to go up. It gets steeper and steeper from here on. So that's why the graph would look like this. So if we were to graph all of the slope of every point from along here, the graph would look like this, taking, again, just the value of the slope. So that's how we made that. And again, we can look at it and understand that if we're doing this, the slope here, it's always positive. The slope is always positive. That means the function is always increasing, correct? Yes. So here, this function is always increasing. It's always going up the entire length. Looking at the graph of the first derivative, we can know that because here, the y values, which are the slopes, or the first derivative, they're all positive. If it was negative, it would be down in this section down here. All the numbers are positive. It doesn't even get close to 2. The closest, or to 0. The closest it gets to 0 is 2. It's still positive. So if you're looking just at the graph of the first derivative, by the fact that all of the y values are positive, we know that it must be increasing everywhere along the graph, the points that we have seen here. So that's one way to tie the first derivative rule into looking at this. In essence, what we did, we could start here. If we didn't know what the original function was, we could look at this and say, well, we know that it's increasing. All of the first derivative values are positive, so the function is increasing everywhere. Now, if we were going to graph the second derivative from this, well, we would graph the derivative of the first derivative. That's a little bit strange way of saying it, but the second derivative is the derivative of the derivative. And if the derivative is the slope, then what we're doing is we're going to, over here, graph the slope of all of the slopes of the first graph. So it's a little bit funny. The second derivative graph is the derivative of the derivative. It's also graphing the slope of the slopes, the slope of the slope. So when we do this here, the slope, when x is equal to 0, well, we could estimate it and say, well, maybe it's going down, so it's negative. So maybe it's at -8. So at x is equal to 0, I'm going to put in a value here at -8. We have a point there. Now at x is equal to 2, if we took the tangent line here and drew this, the tangent line, say, well, the slope is going down, so it's negative. And we could say, well, it looks like it's probably about -4. So at x is equal to 2, I would come down to -4 and put a point there. Here at x is equal to 4, the slope is 0. If we drew the tangent line, it would be here. So at 4, we're going to draw a dot here where the slope is 0, at y equals 0. And if we come up here, maybe to fill in an in-between dot to kind of make sure we're getting the pattern right, at -1, if we took the tangent line, the slope of that tangent line would be probably -6. So we'd come over to 1 and down to -6 and put a dot there. So now we kind of see what's happening. The slopes over here on the positive side are going to be the same basic way. This one is going to be positive, and the slope is going to end up being 4. So it's going to be a straight line. At 6, the value would be 4. 1, 2, 3, 4. So that's here. So now, if we drew the line of this, what would the graph of the second derivative look like? Well, it would look a little something like that. So by taking and plotting the slope at each x value, we would get a straight line when doing this. Now, as we relate this, we realize here the second derivative is negative, right? If this is a graph of the second derivative, over this section, the y values are negative. -8, -6, -4, -2. Well, if the second derivative is negative, that means it's concave down. So in this part of it, yes, it's concave down. Here, when x is equal to 4, the y value is 0. Well, when the y value is 0, we said usually it's a point of inflection. So this is neither concave up nor concave down. After it's concave down, looking at the picture, we know that's concave up. And we can confirm that because after x is equal to 5, when x is 6, 7, 8, 9, 10, and so on, it's a positive number here. The y value is positive. +4, +6, +8, and so on. So that must mean it's concave up. And so it switches here to concave up. So we can look at the different graphs and understand more about each, how they relate together through doing these kind of things. Now, while we did that work in graphing, the reality of it is that we can do this a little bit easier without graphing. if we have the same function here, this 1/3 x cubed minus 4x squared plus 18x plus 10, if we take the first derivative of it here, we get x squared minus 8x plus 18. And if we take the derivative of that, we get the second derivative, we get 2x minus 8. If we want to find the inflection point, we can set it equal to 0 and then solve for x. So 2x minus 8 equals 0. Subtract or add 8 to both sides, we get 2x equals 8. Divide by 2, we get x is equal to 4. So, this is the point where this is where the inflection point will be. Now, if we were trying to find out, is it concave up or concave down, if we did, for example, an x of, a second derivative of 0, which would be like saying we're doing a y double prime of 0, well, we'd put that into this function, right? And we get 2 times 0 minus 8, but that's minus 8. So it's negative, so it's concave down. And in fact, we could do this at different points. We're going to y double prime of 2. We would get 2 times 2 minus 8, which is minus 4. If we did a y double prime of 4, well, we already said we will get 0 with this. And if we did a y double prime at 6, well, then we're going to get 12 minus 8, which is 4. And a y double prime of 8, we're going to end up getting a positive 8. Now we realize that's the same values that we were graphing back here. When we looked at each point, we found out the slope of each line, that's what those values were. So when we come into this kind of situation, we can look at it and realize that, yeah, before when x is less than 4, when the values are 0, 1, 2, 3, and so on, all of the values are going to be negative. The ones over here, it's negative. So it's going to be concave down. And if we look at x is equal to 4, we have this point of inflection. Not writing so well on the board right here. The board's a little bit off today. The point of inflection, singular. And we realize that then when the second derivative is positive, that it's going to be concave up. So that's kind of how we can apply it to these different things. Now, say, using just the first and second derivative rules, can we really get every kind of curve? Well, yes, if we look at, if the 4 different cases, we'll get all of the 4 different kind of curves that we can have. If the first derivative at a is positive, that means the function is increasing. The second derivative rule, if the second derivative is positive, then it's concave up. So if it's increasing and it's also concave up, we get this kind of shape. If the first derivative is positive, of course it's increasing. If the second derivative is negative, then it's going to be concave down, and we get this shape. It's still increasing, but it's concave down. So if we look at then, in the cases where the first derivative is negative, we know that the function will be decreasing. It's going down in both of these functions. And then for point number 3 here, the second derivative is positive, which means it's concave up. So we get this kind of shape. And in this case, the second derivative is negative, so it's going to be concave down, and we get this shape. So we get the 4 basic kind of curves, other than, of course, a straight line, which is technically a curve, but we'll just look at the curves that are not straight. And these are the 4 basic kinds that we will get. So using the first and second derivative rules, we can know how to graph any particular curve. So if we were going to do this, we want to sketch a graph where we have the points 2, 3, 4, 5, and 6, 7. Well, let's put those on the board a while. So the point 2, 3 would be 1, 2, 3 here. Oops, the board's a little bit off, but forgive my funny point. Then at 4, 5, that would be about here. And then at 6, 7, that would be here. Now, of course, when we're doing this, the temptation is to, oh, look, it's a straight line. Well, no, it's not going to be. It's not quite that simple. But what will it do once we use the rest of the information? Well, the second point says that the first derivative at 6, so that's going to be over here when x is equal to 6, the first derivative is equal to 0. Well, the first derivative is equal to 0. We said that's where there's the slope is 0, and it's going to be either a relative maximum or a relative minimum. And the first derivative, when x is equal to 2, is also equal to 0. So that also means the slope at this point is also going to be 0. So as we draw the lines, we're going to have a relative maximum and minimum at these places. Now we can probably guess from here which way it's going to be, but we can go through and be more accurate by doing the third point. And that says that the second derivative is greater than 0. Again, if the second derivative is greater than 0, then that means that it's concave up. Remember, the shape will be this kind of U shape like this. And that happens when x is going to be less than 4. And excuse me, here x is equal to 4 is here, so it's going to be concave up before this point. So that means in this section over here, it's going to be kind of that kind of shape. The second derivative at x is equal to 4 is 0. Well, when it's 0, it's a point of inflection, right? So that means it's going to change from either concave up to concave down, or vice versa, the other way. And then here it says the second derivative at x is less than 0. When the second derivative is less than 0, we know that it's concave down, or this basic kind of shape. And that happens when x is greater than 4. So that's over in this part of the graph. It's going to be kind of like that. Well, even if we kind of come in and put a little cheater here and say, okay, it's that shape and this shape, that makes it pretty clear how it's going to be. So we can graph this. If we have a point of inflection at x is equal to 4, we could start at this point and realize it's going to come down to here. Now, as we draw this, it's usually going to be reflective through the point of inflection. Maybe restate that a little bit faster. It's going to be reflexive on the point of inflection. And that means it's going to be kind of a mirror image. So if we're coming down like we are here, we know that it has to go up in kind of a similar way, and we go up a little bit like that. Now, from this point on, if we did a mirror image of it on this axis, we would draw it the other way. So from here, it's going to go up and look like the other side, just simply a mirror image of it, reflected, so to speak. Now, we don't need to draw on that line. It just gives us, just visually shows you how it's going to be. But if you draw the one side from here to here, the other side should look the same thing, just flipped over. That's what I'm trying to say. And of course, all these other things you don't have to use. You don't need to have, you don't need to have these other things there. But if it's a helpful tool, then we can. A little bit of trouble with the whiteboard there. I'm trying to erase it and it's not doing it. But anyway, I think you hopefully have the idea. If you have questions, you can ask in class. Now, to help solidify some of the connections between graphs, here is a typical revenue curve. Every company has a different revenue curve, but one that's typical across many businesses would look something like this. And this particular one, if we did a graph of the marginal revenue, or the first derivative of the revenue, we would again do the same thing, that when x is equal to 1, the slope is 6, so we put a dot here, and we continue that. And when we're looking at it, we can realize that there really are some connections here that are helpful in understanding. Now, assuming that this makes sense from how we did it before, when x is equal to 2, the slope is 4. So at the point x is equal to 2 here, we plotted this point 4. At x is equal to 4, there was a slope of 0. So we plotted at 4 of y value here of 0 on the marginal revenue, or the first derivative. And then the slope went negative. So again, it's negative down here. At x is equal to 6, the slope was minus 4, so that's why there's a point here. And at x is equal to 7, the slope is minus 6. So at x is equal to 7, we put a value of minus 6. And we connect all the lines in between. We realize it's a straight line. Now, we notice some patterns when we do this. The slopes are symmetrical when x is less than 4 and greater than 4. It's just like it's a mirror image, just reversed. And that would be the same thing here. If we drew a line here, we could take this side and flip it over to here, and it's going to be the same thing here, except instead of flipping it over, we're going to flip it over and then up, and they're both symmetrical. Now, that means the change is constant. Now we notice here, the slope here is positive, and it is decreasing until it gets down to 0. The slope is 0 here. And that's what we have over here in the marginal revenue. The slope is positive until it gets to x is equal to 4, and it's decreasing to that point. After that point, the slope is negative, and it keeps getting, the negative value keeps going, minus 2, minus 4, minus 6, and that's what happens over here. So hopefully this helps you define some of the link. And we notice, of course, that there is a relative maximum here. The slope is 0. And here, at x is equal to, well, I should say over here, x is equal to 4, the slope is 0. So the same thing here. We find there's a maximum here because the y value is 0 at x is equal to 4. So that means there's going to be a maximum or minimum here. How do we know which one it is? Well, in this case, the slope was positive here, and that means that the function over here was increasing. What I'm doing right now is going backwards. If I didn't know what this was, just by looking at the marginal revenue, I could figure out if it's a maximum or minimum. When we look at the graph, it's obvious, right? But if we didn't have this picture, the slope is positive until it gets, the slope equals 0 when x is equal to 4. So if the slope or the first derivative is positive, then it's increasing. So that must mean it's increasing until x is equal to 4. Because the y value at x is equal to 4 is 0, that means that there's a relative maximum or minimum. After this, the slope or the first derivative is negative. All the values are negative. That, if the first derivative is negative, that means the function is decreasing. So it's coming down. So if it's increasing to a point and then decreasing, it must be a maximum. It's increasing till you get to a point, and then it's decreasing after that. It has to be a maximum. And as business majors, you're very interested in your maximum revenue. A little bit later, in a week or so, we're going to go over how to, if you know your typical revenue function, how can you find this maximum or minimum? It's not too hard to do. We'll just put it into business settings. Now, here's a typical cost curve on the left, and then the marginal cost curve on the right. And this marginal cost curve is made the same way. At x is equal to 0, the slope is 18. So at x is equal to 0, we put a dot here when x is equal to 18. At 2, we put a dot at 6. At 2, we put a dot at 6, and so on. Now, when we're doing this, we notice, again, the connections between the graphs. The function here, it's always increasing, right? It's always going up. It slows down a little bit here on the rate that it goes up, but it's always going up. If we look at this graph, we notice this. We notice that here all of the y values are positive. That means the first derivative is positive. That means it has to be increasing over this entire range, and it is. So even if we just had this graph, we can look at it and say all of the first derivative is positive. It is increasing over this whole range. So the original function also has to be increasing over this range. Now, we also notice here that the slope is pretty steep, and then it gets less steep until it gets to this point. So the slope is going down until it gets to this point when x is equal to 4. And we notice here, this is true. The slope is going down until we get x is equal to 4. After x is equal to 4, the slope starts getting steeper. It's increasing, it's going up again. And we notice the values are doing the same thing. They're going up, and it works out that way. So in making the connections between the graphs, this is the kind of thing we're looking for. We can get an idea of what this graph looks like from just this graph. The last point I want to make about this is that we know that we have a point of inflection here. This is the first derivative, which doesn't tell us about inflection points except for the fact that we know that the slope of the slope, when the slope of the slope is equal to 0, then you have an inflection point when the second derivative is equal to 0. The second derivative is going to be the slope of the first derivative. So here we know that the slope is 0 when x is equal to 4. So that tells us that we will have an inflection point at x is equal to 4. And that does happen here exactly that way. Now, with this kind of cost curve, it's a little bit something to analyze. Earlier with the revenue curve, we said we were very interested in what the maximum revenue was. Of course, we always are. Finding the maximum profit is extremely important. Finding the minimum cost is important. Well, what about the inflection point? Is there any significance to that? Well, there is, but it's dependent upon your individual business and also the kind of business that you're in. We notice that up to the inflection point, the rate or the marginal cost is steep here, and it becomes less steep. The slope is 18, it keeps going down until it gets to 2, then it starts going up again. Well, you're interested in this point here when it changes. You like it when your costs slow down, and the difference between here, producing from 0 to 2, is pretty great. But the cost difference from 2 to 4 here is not as great. So that's a good thing. It means you're producing more items with an overall less. Overall the cost is greater, but if you look per item, the cost per item is cheaper. Now, after this point, the costs start skyrocketing. They go up very quickly again. Why is that? There's no one set answer for this. You'd have to apply it to your business setting and figure out what it is. Maybe there's things that are happening. Maybe what's happening here is you have a couple of employees and you add a few and you find your production increases more quickly and your cost goes up, but maybe working with 10 people is more efficient than working with 5 people, so you get more produced in the same amount of time. Well, then at some point you say, well, we need more people, but we can't hire more than 10 people at a time. So what we're going to do is we're going to start 2 shifts. We're going to have a day shift and a night shift. Well, then of course your overall costs are going to go up, because here was your cost of hiring the first shift, and now it's the cost including the second shift. That may be a good thing. Depending how this cost goes, you may just want to do that, or maybe you want to get another machine. It's possible that this is the cost for it's a little bit of a different scenario, that you started out with working with people here and then you bought a machine, and machines work a little bit more efficiently, so your cost per item made went down, so it cost this much, but you maxed the machine out. So then maybe here you want to buy a second machine so you can produce more goods over the same amount of time. The cost will go up, but the cost of the machine immediately is steep because you have to pay for the machine, but then the more you use the machine, or the faster the machine runs, the more output you get in the same amount of time for basically the same cost. Then the second machine, initially it would be expensive, and then it's going to level off and become very efficient. So it's an important point. When your costs level off and begin to increase, then you maybe need to figure out what you need to do. It's also possible that you maybe opened up a second location, so your cost went up. It's something you want to be aware of. Why did the cost go up? Maybe in these cases, it's something generally that's good. You're increasing your production, and it's a good thing. But it's also possible that it's not good. In this case, if you're producing up to 4 units you're doing really well. But then again, your costs start to skyrocket. Maybe that means that your method of production for making smaller quantities is good, but it's not adequate for producing a larger quantity, say 10 or more. So you may need to look into another production method. You may look into simply reducing cost. Is there a way to reduce cost so that producing 10 units will not be so expensive? So it's something to pay attention to. You could save you some money, or your business some money. Now, in looking at the connection between graphs, here is a graph of the derivative. Could we actually figure out what the original function looks like based on this information? What is the slope of the graph when f of x equals 1? Now, as I hope you have picked up, in the original graph we did an f of 1, and f prime of 1, we used the same x values. The y values changed, but the x values were always the same. So when here we have an f prime of 1, that tells us information on the original graph when we're doing an f of 1. And an f of 1 is, of course, in the original graph when x is equal to 1. So what's the slope of the graph? Well, the graph of the derivative is a graph of the slope. So the slope when x is equal to 1 on the original graph is the y value here on the derivative, and that's 2. So we look at it and say, oh, okay, the value is going to be 2 at this point. Now, describe how the values of the first derivative, this graph, change from 1 to 2. Well, here it's 2, and it goes down. And if it's going down, it must be, the values are getting smaller and smaller, until it gets down to this value about of 1. So we'd say that the values are decreasing, but they're all positive. Nothing is negative until you get a greater than 3. So between 1 and 2, the values are positive, but the values are decreasing. Well then, what's the shape of the original graph over the same interval? Well, the values are positive, so that is going to mean that the original function is increasing because the first derivative is positive. Now, the slope is decreasing as it goes, so that would mean that if we were looking at this kind of shape, because it's positive, we know that the function is going up, and since the values are decreasing, the slope is going like this and then getting smaller and smaller, so we know that it's going to be this kind of shape. It's going to be concave down over this range. Now, for what values of x does the graph of x, f of x, have a horizontal tangent? Well, again, horizontal tangents is when you have a maximum or minimum, and that happens when the first derivative is equal to 0. Good, you remembered. Where is the first derivative equal to 0 in this graph? Well, that would mean where this line crosses 0 for a y value. It's where it crosses the x-axis, and that's at x is equal to 3. So we're going to have a maximum or minimum at x is equal to 3. Why does f of x have to be a relative maximum at x is equal to 3? Well, we said it could be either or. Apparently there's a way to figure that out from this graph. Well, we have a maximum or minimum at x is equal to 3. Before x is equal to 3, all of the first derivative values are positive. That means it's increasing. That would mean that it's going up to that value. After that, after x is equal to 3, the first derivative is negative. All the y values are negative. And if the first derivative is negative, it means the function is decreasing or going down. So if before x is equal to 3, it's going up, and then we have a maximum or minimum, and afterwards the values are going down, x is equal to 3 must be a maximum. So we know it just simply by using, in this case, first and second, well, just using the first derivative actually here. We didn't even use the second derivative. So, is this right? Well, let's look on the next slide. Now, for some reason, like this came out backwards. The red line is actually what was blue on the other line. It's the graph of the first derivative. And again here, at x is equal to 1 is a value of 2. and at x is equal to 3, there's a value of 0. Well, again, that's where we have the relative maximum, and this section, the values are all positive, so it's increasing as we get up to that point. After x is equal to 3, the first derivative is negative, which means the original function is decreasing. So we have this kind of thing happening. So we can describe this graph and know that this is what's happening. We don't necessarily have the points in this, or actually, yeah, we don't have the points, the y values for this, but we know that the graph is in this general shape. So hopefully this makes sense, and the homework helps to solidify this somewhat more. And the homework comes from section 2.2, and again, this is on Moodle, and we'll see you in class.